Hello and welcome to the webinar of Würth Elektronik ISOs. My name is Eleni Stark and I will moderate the webinar today. We are very pleased that you took the time to participate in our webinar. Our speaker today is our development engineer Laurent Völkel. He will hold today's webinar on how to select the right EMC ferrite and also answer your questions. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you can't ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. Please also indicate the slide number from the presentation in your question, so that we can easily relate your question. The slide number is located in the right corner and top of the presentation. The webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 15 minutes in addition scheduled for this. If we can't answer all your questions within the 15 minutes, your questions will be answered by email following the webinar. The recording of today's webinar will be available one day after the webinar on our Ask Laurent website. And now I'm giving directly to our speaker Laurent Völkel, and I wish you an exciting webinar.
Hello everybody, my name is Laurent Völkel and I will talk today about ferrite selection, how to select the right chip bead ferrite for your application. Well, first of all, I want to show you that I will go a little bit deeper in some application and also some classification electrical parameter, and I will take care about some saturation point and inrush current, and last but not least some layout recommendation and some tools. But what is the reason why you should use a ferrite bead? Well, first of all, normally you are building a device and you go with this device in the EMC lab to check the EMC performance. And if you have a little bad luck, it could happen like this, that you're exceeding some parameters, some levels, and then, well, you should not start to cry. First of all, try to check what is the maximum peak in your scan. When you see this maximum peak is roughly something by 200 megahertz and you have a peak which is almost 20-21 dB, always try to filter this frequency. When you filter this frequency, all the side effects from this filter, because you will not have a filter which is cutting exactly only 200 megahertz, it will also filter all some harmonics additional. But this is a long way to that. First of all, we have to take care about the different filter topologies, because you have different system impedances. If you are connecting low system impedance with high system impedance, normally I always start to make some filters and I start to use a LC filter. If I see that the LC filter doesn't give me enough effect which I expect, then I give a second capacity, so I play a little bit with the capacity in accordance to the frequency which I want to achieve. And when I see that the two capacities, so I have now a P filter, not given enough results, then I try again the LC filter with an additional L, so I give a second inductor. In fact, I did build my T filter. So the T filter or P filter or even the LC filter, if is recognized that is a differential noise, because first of all you have to know it is a differential noise. For a common mode noise it will not affect too much, and you know exactly where the noise is coming from, which is also not so easy to find, I know, then you can try to use this LC, P or T combination. For the capacity, I recommend to use small capacity values, maximum 1 microfarad. Nanofarads are much better, but always if you use for the LC filter inductance, please check the inductance Q factor value. You should have inductance with low Q factor because you want to filter, not to store energy. And always double check the self-resonant frequency of the component to avoid kind of mistake that you're building oscillators and instead of having less peaks you will double the number of peaks. For the Q factor, maybe some of you did forget what is the Q factor definition. It is the XL divided by R, so the impedance reactance divided by the resistance losses. For an inductor, normally with higher frequency the Q factor is increasing, so it means is a fact it will be not so good for filter. For ferrites, especially for ferrite beads, we are producing them in that aim that they should have a low Q factor. They should be lossy products, not good to store but very bad for storage and very good in case of that for absorbing or to filtering. Normally we can say a ferrite bead is kind of frequency dependent resistor. Remember, for storage you will have a high Q request, and for filtering, for the inductance, you will have a low Q request. Now if you look in the data sheet of the ferrite beads, you will see some different curves like XL, R and Z. Actually there are three different areas. One of the area is the inductive area, where it's not so much losses, it's more reflecting, it is that kind of impedance reactance. And then you have a resistive area, and when the maximum or reach the phase shifting happen, then you have this self-resonant point where it's capacity working. Actually on the maximum point, the XL, it is equal to the XC, and after the XC, because it's multi-layer, you have a capacity in the layers, you will have a bypass to the high frequency. How is possible to measure impedances? Well, this is not a trivial measurement. Normally you need an impedance analyzer with a calibration fixture and calibration system. You calibrate in a 50 ohm system, and this impedance measurement machine actually is measuring above the frequency, the XL and the R, and then make a visualizing. It's actually a calculated value of the impedance in fact. The equivalent circuit of ferrite beads, like you can see here, is LRC in parallel. The current is lazy. He will take always the easiest way. If you have a low resistance, take the resistance way. If you have a low impedance of the inductor, we take the inductance way. As soon as you have reaching high frequency and the capacity is big enough, he will not go to the R and L, he will go to the C. In terms of ferrite beads, you will find different ferrite beads manufactured for wideband effect, and some of those are made for high speed. It means in a low frequency, to bypass a high frequency signal, they have no effect, but they have a higher frequency response, and they will have much more peak impedance in high frequencies. So now we go back to the application. Actually, you remember the EMC measurement, you have this level of the EMC requirement, radiated emission, you make your first shot, you know you are failing, then you go home, you want to cut this 20 dB from somewhere, you find out this is on the VCC cable, and then you're calculating the right ferrite inductance according to some calculation. You put it in and you go back to the EMC laboratory with your redesign, and you wish you are going back and you will pass the EMC test. But my experience is, like, if you are going on EMC lab on Monday, it could happen something like that. You are still fail. You have less peak, but you still fail. So Monday is not a good day to measurement. If you go to the EMC lab on Friday, maybe your Friday is more lucky day because you want to go to the weekend, you want to finish the job, and you make the EMC measurement, and you're, wow, excellent, you're below the limit, everybody happy, and this is the Friday measurement. Well, you could say you are below the limits, yes, it is okay, but if you pay attention, you will see that you have very, very weak safety margin in this area. I will not stop to experiment in that point, and I will not say, okay, CE certified, put the logo on it, sign the paper because it's okay, because that could happen that in some other components which have tolerance and also manufacturing have tolerance, you will not meet the requirement, and then you have to pay the penalty or you cannot sell the product. I will say, how about if you go to measurement on the EMC lab on Friday, but this is not a simple Friday, it is the Friday before you start your summer vacation, summer holidays. You can imagine you're going to the EMC lab, it's Friday, and beginning for the next week, so you will have 2 or 3 or 4, even 4 weeks holiday, and then you make a measurement and you reach that point. When you reach that point, please don't focus on your device. Focus on the EMC engineer. He starts to be nervous. Some of those, they're looking really if your device is switched on. Some of those will start to check the antenna, if the antenna is connected to his receiver, or even open the door from the EMC chamber to see if his machinery is working. When you reach that point, you can congratulate yourself. You are doing an excellent EMC job. Now you want to know how. Not so easy to, I don't have an algorithm for that. But maybe you can try when the EMC lab is measuring, they give you information about you have to go 40 dB down or 20 dB down, how to take this dB into the impedances. Well, we have the system attenuation equation, and actually you are looking for this ZF, it means the filter impedance, and you can calculate this in this formula. You just have to take out ZF from logarithmic, put it on the front, make an equation in exponential, but even that not helping too much, because to use this formula you need 2 additional information, and this information is ZA and ZB, source impedance and load impedance. Well, in a university it's simple, everything is 50 ohm. But in real world, you can imagine you are manufacturing something like a small remote control. You put this remote control to the desk and they exceed 20 dB the limits, and now please tell me what is the system impedance of this remote control. Oops, not 50 ohm anymore. What now? Well, this is not so easy, but you have to start with some real values. Let me see like that. If your system impedance is according to the power supply, a power supply, VCC, have a system impedance roughly something 10 ohm, very, very rare 20. If you're working on some data lines, if you see the noise on the data lines can be more like 50, even higher, like 90 ohm system impedance. If you want to filter ground planes because you are splitting digital ground to analog ground and you put these ground points together, well, ground to ground connection system impedance will be less than 1 ohm. Don't try to use ground plane which have more like 1 ohm. Normally milliohm is much more welcome. So now you know you have something like a VCC power line where is the noise, it's coming from the DC-DC converter or coming from outside. Then you can consider the system impedance and you can assume this is roughly 10 ohm. If it's a buck converter, you will see it's even less, but 10 ohm is a good starting point. Now, if it's 10 ohm system impedance, I have here 1 ohm, 10 ohm, 50 ohm, and 90 ohm system impedances. And you're looking for 20 dB. So if you're looking for 20 dB, it means if you put the scientific calculator to operate and you will calculate with a 10 ohm system impedance, you will have a value of something like 180 ohm for the ferrite beads. So I will start with this point, 180 ohm. And if you see that this 180 ohm is giving too much filtering effect, you can be happy, because you achieve even more like 20 dB attenuation. If you see that this is giving only just 10, 15 maximum, then maybe your system impedance was underestimated. Maybe your system impedance did a bit higher. If you have data line, to achieve 20 dB, you can see you need much more at the 50 ohm system impedance, more like 1000 ohm ferrite impedance to reach 20 dB. So it depends always on the system impedance, how much impedance for a ferrite you will need to reach this damping. Now we can go in some application and we consider a data line. For the data line ferrite beads, you have to take care again that it is a differential signal and you have a differential data signal as well. The ferrite bead should be chosen in that way that your signal, your main signal, should be not affected for the impedance of the ferrite. So it means the ferrite in that frequency where your data are transmitting should not have too much attenuation, else you will damp your signal as well. For the harmonics, for the noise which is generating the third, fifth, seventh harmonics, when you want to cut them, then it's okay to have a high system impedance, high ferrite impedance, but not for the data signal, because you don't want to filter your data line as well. If you have more like one data line, normally you have to filter each one's line, not only one. If it's a data line with just one single pair, then you can filter only this. You will see that the ferrite beads are divided in many different categories. We can say we have some high speed for more for data lines. We have some wideband, which is quite already on a low frequency, quite very aggressive, and keep that as wideband as possible. And then we have some high current definition, because high current we define all the ferrite beads which are able or capable to carry more like 1 amp current. And then we have some special manufactured high frequency one, which could be again high speed wideband or even high current. The high frequency one, they are totally different manufactured in a completely different multilayer. It's not like a sandwich, it's more like a spiral from pad to pad. You have to pay attention especially that the ferrite beads, which is below 1 amp current rating, that the rated current of these ferrite beads is defined on the delta T of 20 Kelvin. It means the ferrite will self-heat of 20 degrees above the ambient temperature if you apply this current. Like you see here, 500 milliampere on the first option, and you will have a delta T of 20 Kelvin on this ferrite bead. It means if you have an ambient temperature of 125 degrees Celsius, you cannot apply this ferrite, because if you apply this current to the ferrite, he will have already 145 degrees Celsius. So in this case, you can admit an ambient temperature of maximum 105 degree, and you put the maximum current, you will reach on the ferrite bead 125 degrees Celsius, which is fine to him. It doesn't destroy. For the high frequency one, you can see already sometimes it's just 50 milliamp, and already it's running out of his performance if you reach higher temperature. For example, for slow speed signal like RS232 or 485, you can use the wideband version. It's no problem to use them. As soon you have some very high speed signal like USB 2.0, 3.0 or HDMI, definitely you have to take care about the ferrite beads, because already the ferrite beads start to acting 1-2 megahertz, and then you have to choose ferrite beads which acting only above several 10-20 megahertz to not attenuate too much the signal himself. Else you will have a problem that you will filter the noise, but you will filter the signal himself as well. Another application for ferrite beads very often to see, it is to slow down this ringing or the slew rate on MOSFETs. Well, if you have a very high rise time and you want to slow down a little bit because you have this ringing on it, this ringing is because of this capacity between gate and source, and just to put a ferrite bead to here, well, it is possible to use that ferrite bead, but now you have again to pay attention. If you put here a ferrite bead, you should choose the ferrite bead not in the area where the ferrite bead for this is acting like XL, not on the inductive area. You should use the ferrite bead which is acting in the R area, in the resistive area, because this is much more better, and you will see in the next features why is that so important. We did make some measurements on this rise time, and when we apply a 0 ohm resistor, we had this high peak and the ringing. Then we apply a ferrite bead with 600 ohm, and we saw, okay, it is less, but the ringing still was there. As soon we did apply a right ferrite, this time was a 2.2 kilo ohm ferrite bead, the rise time was not so bad anymore, the ringing was not so bad anymore, and it was quite okay. But we achieved the same effect if we put just a resistor 16.2 ohm, the same effect like the 2.2 kilo ohm. The only one thing was the resistor is also, well, the efficiency will be not so good because the ferrite bead have not so big DC resistance. You can see here on these emission scans that when you have this ferrite bead, you can have a much better high frequency area. In this area, in the high frequency, you have less and less problem in comparison if you just have nothing on this MOSFET. I just want to mention, I see on my time that I'm a little bit talking maybe too slowly, whatever. I will over time maybe 5 to 10 minutes this webinar. Well, for power line selection, it is important that for power line you are selecting the right ferrite bead in accordance to the current which will go to this VCC. For a power line, all the ferrite beads which has a current possibility to carry more like 1 amp, we define them with a delta T of 40 Kelvin. So not 20 Kelvin, 40 Kelvin. It means if you apply to this ferrite bead 2 amp, himself will have a self-heating of 40 degrees Celsius above the ambient temperature. So this 40 Kelvin additional to the ambient temperature. That means that you have to take care if you have an ambient temperature like 85 degrees Celsius, you can still apply the maximum current. As soon you have a higher temperature like 100 degrees Celsius, you must derate because the maximum current at 100 degrees Celsius will be only 60% from his initial, because else it will be too hot, and maybe you will find a way to see that the ferrite, if it's going too hot, it could be desoldered by himself and run away from the PCB. The DC BIOS also, it's very important to take attention, because if you talk about more current like 500 milliamp, you may see that the ferrite beads are influenced with this DC BIOS load. They start to saturate because they are very, very small and tiny, and they are closed, completely closed enclosure in the ferrite body, and they cannot escape. This current generates a magnetic field. You can see here the ferrite bead measured by 0 DC BIOS load, like in all data sheet which you will see in every manufacturer. They are defining in a data sheet all the impedances by 0 DC BIOS load. Now you apply 600 milliamp, it will be the blue line, and if you apply the maximum current 3 amp, you can see how much is damping. Now in the data sheet you had 100 ohm, and at 3 amp you have even less than 10. So this is reality. But honestly, all the data sheets are measured in a 50 ohm system impedance. I can imagine that one of you did build a 50 ohm data line with 3 amp. So when you have the 3 amp, it's not anymore 50 ohm. You may have a very, very low system impedance like a power supply, less than 10 ohm, and then these damping losses which you are going in the saturation, it will be compensated because your system impedance is much lower. But how much it is saturated, you cannot measure it except you invest 20,000 euro additional to your impedance analyzer, which costs already 60,000 euro to make this measurement. Or you just open in a simulation software like LD-Spice. It's a free of charge software from Linear Technology, and we have a model with all this measurement, this Z in bracelet I ferrite bead. This model contains all the ferrite beads which has 1 amp or higher current rating, and you can see in the simulation, which is actually measured value in 401 measurement point from 10 meg to 1.8 gig. This is what is guaranteed calibration from Agilent, now Keysight, with a step parameter from 0 amp to 3 amp in 500 milliamp steps. All these values you will find in this simulation software. And this is one example. Like before, you can see in the example again, 0 BIOS load until to 3 amp, how much damping it will lose. And if you choose this component in your device, you can see if this damping in a simulation already, it's enough for you, or maybe you should use another one. The influence of the ambient temperature is also important to take care, but is not so much influence like the DC BIOS load current. We make some measurement in the thermo camera and thermo chamber, and you can see here minus 55 degree plus 160 degree. The only one thing what is losing the maximum peak of the impedance. They will go with a higher temperature decreasing in the impedances. This is another example for again minus 55 to 160, so you can see the maximum point, it's a little bit less. Another very important point is the INRUSH current. It's a multilayer ferrite beads which are with the layers, very thin silver layer inside build, and if you apply a very high surge current or load dump like automotive guys are saying, you have to take care that this capacity on the beginning is completely empty. And now if you have a source like a car battery and you apply to this capacity until he will be charged, he will take the whole energy which can be supplied from the wire including the battery. So it means it will have a peak current, and this peak current could make from the ferrite bead something very strange. Sometimes you see a nice spark, sometimes you smell something like bad eggs, or you can see some nice holes in the ferrites. That happens when you apply a pulse current to the ferrite bead, and this is not good. What to do now? Well, first what you can do to put the capacity on front of the ferrite beads, and this is a nice solution, but if you want to have some component which can withstand this pulse, then I will say it's better to apply some other components. Now some picture from our TQM from computer tomography made on some nice effect what has happened if you apply 40 amp pulse only just 1 millisecond to 0.0805 size. You can see that sometimes the layer is disintegrate inside the ferrite bead, so it's very nice pictures. Well, to make this INRUSH current, well, we did manufacture something very special, because we start to think what can we do to avoid that kind of high surge pulses to the ferrite bead and make them a little bit more robust. And in this way we did make these ferrite beads which are in the standard series. You can see in the data sheet we say do not use this part beyond the rated current, as will be very excessive heat generated. And the one solution could be really to just move the capacity of front of the ferrite bead, and that helps a lot, because then the current will charge the capacity, and after that will start to run to the ferrite bead and not 10 microhenry charge through a multilayer component. Another solution could be to use this muscular beads. This is a huge peak and huge current which can withstand. This is the multilayer power suppression bead. You can see the layer is in a different way made like the standard multilayer, and also the layer thickness is much thicker, and we have 10 times lower this resistance. And with this construction we can admit 20 times higher peak currents through these ferrite beads, and they will withstand this pulse because we did test them before. So you can find all this information for this MPSB Ferrites into the REDEXPERT software, which is also available on our website. The typical specification, it is that current is standard 3 amp style, which is just running continuously, but it will not be destroyed if you apply something like 20 amp through him or something like that. You can see even the number of peaks, the maximum current, the number of pulse applied with a 10 seconds time, and you can see the pulse length and everything. You can have all this information in the data sheet or also from this REDEXPERT. But also if you look on that component, and you will see that the DC resistance is really extremely low, sometimes just few milliohms. It is very important that you not use continuously above the maximum rated current which we admit into the data sheet. A pulse is a pulse, it's not something which is a continuously current. If you want to do that, then you should forget the multilayer, you should use a wired component. And we have this kind of different wire wound component which have not this problem for pulses and also even repeated pulses, because they are withstand without any problem, because it's a simple copper wire. They are bigger, of course, they are not fit to the small size. You will not find them in 0603 size, but you can withstand a much larger current, and they have also very low DC resistance. And if you apply such big pulse that you will kill these coils inside this copper wire, then you don't talk anymore about normal designs or standard EMC or standard load dump. What I would recommend to you additional, take care of the pattern, of the land pattern of the soldering pads, because if you make the soldering pads too big, you will occur some kind of tombstone effects. The next point is you should place that ferrite beads not close to the edge, because this edge, this kind of flexing stress of the PCB could cause sometimes some cracks. These cracks will make open circuit because it's cracking almost in the middle or on the pad directly on the termination. You should take care about that. We have some recommendation of that. You can find all this information on the website or even sometime on data sheet as well described for this banding and how to place for the ferrite beads to the PCB. More information about these ferrite beads you can find in our website. There are many different ferrites available from us, not only just ferrite beads. And design guides in the REDEXPERT, if you just click on this link on the PDF, which will be available on the website as well. Of course, also the recording. You can see all this pulse effect, and you can find much easier the ferrite bead because you have the possibility to put many fragments. It's not only just 100 like a data sheet, and then to filter which is good for your application. I would recommend one of these books. Depends if you're doing the LT Spice or just want to know more about connectors, about magnetics or ferrites, or about power modules or capacitors. Please feel to ask us or our salespeople for providing you this kind of books. They are very good described from engineer to engineer. If you need examples, of course, our salespeople will be very happy to give you some examples free of charge, of course, and we have also some lab racks and example kits for different component size. If you want to keep in touch with me, I'm also in LinkedIn and also in Twitter. On the landing page of Würth Elektronik site, you can have some more information and some tutorial like a YouTube video or something like that. Now I will check if there's any question about this presentation. I apologize again for over timing. One question was asked, why is the storage temperature only -20 degrees plus 60 degrees and operating temperature -55 plus 125 degrees? Well, this is quite very simple explanation. When we are delivering these components are in tape and reel, and believe me, even if you have in deep Siberia a warehouse, you will not have in your warehouse -55 degrees, and you should have some heating there, because if you freeze the plastic too much, you will be not able to handle that. And as well, when you're taking the tape and reel from our warehouse and you want to store that in somewhere in Sahara, in Africa or in Dubai, you may have not above 60 degrees in the warehouse, because a warehouse with 125 degrees is quite very expensive to store anything there. And believe me, if you just have fun, take the tape and reel and put at 125 degrees Celsius, but not from Würth Elektronik, from the competitors, which they say, or maybe a different way, into your oven and let solder them after that. So this is the only one reason, because we say -20 degrees to 60 degrees. After you take out the components from tape and reel and you place on a PCB and get soldered, it's starting the operating temperature. Doesn't matter if you power or not power on, they should not exceed plus 125 degrees Celsius, and -55 degrees Celsius, it is because our chamber can also go down to -65. So if you will use at -75 degrees Celsius, I don't believe that electron will frozen. Maybe you have some different problem for that. Okay, next question. What is the definition of different ferrite beads like high speed and wideband? Well, we did make this definition from our own. We saw that we have over 4,000 different products for ferrite beads, and we did decide each ferrite which has in the lower frequency, means less than 10 megahertz, less than 10 ohm impedance, they're good for high-speed signals. For ferrite beads which has already a 10 megahertz, more like 100 ohm or even something like 80 ohm, we define them, they are quite very wideband, because they are not only a 10 megahertz 100 ohm, they can keep this 100 ohm above 500-600 megahertz up to 1 gigahertz, and they are very, very wideband. That's just the definition of Würth Elektronik. The high frequency, where you will see CBF, HF, the high frequency, we just want to signalize they are manufactured in a totally different machinery. They are not layers above the layers from bottom to the top. They are layers to layers from pad to pad, like a spiral inside. And in that way we can achieve at gigahertz still a very, very nice impedance, but they are totally different manufacturing standards. I hope that was the explanation enough. So I will see some other question which I will answer then personally by the email which will get registered. And now, because of the time, and I hope you will enjoy it, I will close this session and hope you will see me next time. So I will say bye-bye.